Okay, first of all, thanks to Karna and Maritina for organizing this seminar and introducing me and moderating the seminar later on. I guess the introduction regarding myself was already given by Maritina. Maybe I can say a little bit more about Altera. Altera is part of Wageningen University and Research Center. We do education and research in the area of life sciences, and Altera is specifically aiming at what we call the green environment, which is quite broad, goes from environmental science to soil science, agricultural science, water management, etc. So quite a diverse area of domains. Let's see. First, a small outline of the presentation. I would take a look at the historic perspective of big data in our domain, tell something about our expectations for the near future, give some big data examples from the agri-food domain to, let's say, show what kind of problems we deal with and how we tackle that. And I will talk specifically about some big data challenges, specifically for our domain. I will finalize with something about the expectations that we have versus the current reality, which kind of states, let's say, the state we're in right now regarding big data. So if you look at the historical perspective, then you can see working with this broad amount of domains, crop science, animal science, food science, etc. Quite early in the 1960s and 1980s, there was a lot of institutional data collection. So institutes were doing their research and collecting their own research data. And around, let's say, the 1980s until 2000, there was a lot of developments in computer models, which also, of course, meant that except from, let's say, collecting data from the field, a lot of new data was generated with those models. So this is where, let's say, the big data thing maybe started a little bit already from at least the modeling perspective. Around 2000, there were a lot of institutional applications developed regarding, for instance, impact assessment and all kinds of, let's say, policy and decision support applications. And that was for us also the area of integrated modeling frameworks, where we tried to combine models from different domains with different scales, etc. Then the last few years we had a lot of improvements regarding, let's say, how to work with this bigger amount of data. We saw, let's say, development of the practice of providing good metadata with the data, which is very important for us. We also saw the development of semantics and linked open data. And what we see right now, that is a lot of open data becoming available across sectors. Of course, there are a lot of policies and movements that support open data. So we see that even more and more data is becoming available at this moment. And towards the future, we expect that a lot of emphasis in our field is going to be on, let's say, combining all those multidisciplinary data. So we deal with a big data pool and a linked data pool across disciplines and requiring strong computational capabilities to process those. So on one side we have, let's say, the ICT hardware-like developments, the grids, the distributed storage facilities and stuff like that. On the other side, we have a lot of new data sources which are becoming bigger and bigger and faster. For instance, remote sensing, crowdsourcing data. There's in genetics, rapid phenotyping and all the omics areas, social media, of course. And the big question for us is this a potential to solve all kinds of problems in agriculture, nutrition, food security and climate change, which we currently cannot solve because we lack the data and the capacity to process all this data towards, let's say, information for decision making. So another way to look at it is through this pyramid. That's already quite an old concept published in many papers, and we just revised it a little bit to, let's say, reflect our own domain and the issues we deal with. At the end, most of the time it is about, let's say, supporting decision makers, supporting policy makers in all kinds of sectors with let's say, information they need. Starting with, let's say, the raw material from sensors, from databases, from satellites, etc. So that's, let's say, the part where the data is. Then we have an information layer where we usually add meaning to this data, try to connect it in a sensible way. That's also where semantic web technologies, linked open data, etc. are coming into perspective. The next step is then, of course, to generate knowledge. So you're talking more and more about decision support systems, modeling, cost-benefit analysis, so all kinds of tools to again, let's say, provide added value from this information that we generated. And at the end, and that's well, generally called the wisdom level, which sounds a little bit big maybe, but that's where all the knowledge is taken, and where a lot of, let's say, interest and all kinds of intangible things like values, preferences, trade-offs come into play in order to, let's say, take this knowledge and make it into integrated decisions or policy measures. So if we take this to a specific example in our domain, then you can see a little bit more of the details of this concept. I take the Mars system, which is a system we developed for the European Commission, for the Joint Research Institute, and what they do with it is they calculate crop forecasts, so predictions of the yield of crops in Europe and on a global level. And it was originally designed to provide information and to take decisions on the common agricultural policy. I mean, in the past there were a lot of subsidies, and it was very important for the Commission to more or less know how much wheat, how much other crops were going to be produced over Europe to be able to, let's say, sense what will be happening also financially regarding subsidies and stuff like that. In the last few years also, let's say, the emphasis on food security has become stronger and stronger, so there are global applications to check, let's say, developments regarding crop yields in, for example, in Africa, which is quite a focus at this moment. So it's kind of extended from just a European policy tool to, let's say, also a more global policy tool. If we look at this pyramid, then we start, of course, again with the data. The system takes data from weather archives, it takes live data streams, information from crop and soil databases, and information from models that pre-process data for the system. And that all has to be, let's say, connected, and we use all kinds of procedures like rescaling of data to one specific scale through interpolations. We use GIS systems, crop models to, let's say, come from weather data and crop characteristics and soil data to the yield developments through the year. Then the next level is using statistical tools and data mining and reporting tools, decision support systems to generate the end information required to take decisions on the European level. So what comes out in the end is something like this, which is a Mars bulletin, which has all kinds of information and advice on how to let's say, deal with crops, what is going to happen in specific areas in Europe, if there are any problems expected, and things like that. So that's the policy and decision making level. So this is an example of a system that has characteristics of big data. I mean, it processes a tremendous amount of data. It's also, let's say, the velocity aspect is relevant, because, let's say, this information has to be available for the European Commission within a day, more or less. On the other hand, it is a very, let's say, classical monolithical system. So it's built for this specific purpose and it can only do that and nothing else. So it's also, let's say, a classical system and not to be compared with the more innovative systems that are currently developed around big data. So what we use at this moment in those kinds of systems are relational databases and geodatabases, but also, let's say, plain file-based and Excel data sometimes. Of course, the old proven programming languages like Fortran, C++, Java, etc. You have to remind that especially the models behind those systems are really, let's say, developed in decades and are really legacy software more or less, and it's really hard to let's say, rebuild them into more, let's say, innovative environments. So we usually deal with quite old modeling software, for instance. For remote sensing, we of course have all kinds of dedicated tools and environments for processing and analysis. We use GIS and spatial analysis packages, and we have harmonized information, so some kind of alignment of data models, but that's still very much on, let's say, a single discipline here. We also use optimizations, of course, for storage and computing, but those are quite localized. So we have local servers and storage facilities, and we don't do anything at this moment in the cloud, for instance. So towards the future, we see, of course, the development of high-performance clusters and grids, which could be used to parallelize, for instance, the modeling and analysis software we use in those kinds of systems. First steps are made to do those kinds of actions in our domain, but it's very immature at this moment. We have RDF databases to link data, which is very promising, but seems to be more applied at this moment on bibliographical data and statistical data, and not on those big data sources in our domain. We have vocabularies and ontologies, where a lot of development was, of course, done in the last, let's say, 10 years. So it means that we could, in principle, annotate our data and metadata to make discovery more advanced and to also be able to combine data better than we can at this moment. And we have semantic technologies and natural language processing algorithms which could help us also innovate. But on the other hand, it also seems that agro-environmental research is kind of a wicked domain, which has very specific challenges. I cannot fully oversee if that's fully specific for the agro-environmental domain, but let's see. I'll talk a little bit about that. So I'll do that using, let's say, the V's of big data, which you're probably familiar with. And variety is one of them. But first of all, again, I'll take the pyramid as a reference. First of all, of course, we have obviously volume, especially in the lower part of this pyramid. We have a tremendous amount of data available, and we have to deal with it. I don't think that that's really a lot different from other domains, so I'm not going to go into detail about that. But the other thing is velocity. I also mentioned the example of the Mars system, where we had to have the knowledge in place, let's say, within a day from the data coming in the system. That's also something we can deal with quite well at the moment. I think the real problem lies, for instance, in the variety. So if you look at, let's say, our systems, then we usually deal with a quite broad range of domains. Well, in this example, I take agronomy, soil science, and climatology, which actually are still quite close together. It can be much more extreme even, but just as an example. So then you can see that variety and let's say the difference in data formats, data standards, semantics, etc. is going to play a much bigger role because you want to combine data from all those quite different domains with quite different standards. So, like I said, it's interdisciplinary area, agro-environmental research. From the, let's say, the decision-making policy level, there are very different objectives that are targeted, very different incentives. On the other side, we need to work with quite different data formats, combining them. Those data formats and data sources use all kinds of different schemas developed by different people who are not connected. So there's an issue. There's also a level of standardization which is different over domains and even in subdomains. And we also face different granularities. I will talk a little bit more about those in some examples. Well, you can imagine cases where we work with data from agronomy, climate, water, irrigation management, economy, etc. If you look at, for instance, something like crop yield forecasting. So these are really very different domains with different kinds of data and different semantics. So semantic alignment can be quite problematic in our domain. There are some things like different domains use different semantics. That's logical, but it also appears that they use different semantics to describe the same knowledge sometimes. So then it gets really hard to make your decisions at that level. Semantics may be different and may use not recognized standards, or standards or semantics might not even be existing. We deal with let's say semantic-like structures that are not let's say defined according to the common standards. So that means that, for example, ontology alignment tools, which could be of great help when connecting all those different areas, usually don't work because you face all kinds of different formats and unstandardized formats. And manual alignment, of course, is very resource consuming. So even with the tools, it would be resource consuming, but that could be a big help in reducing that. So it's resource consuming, but it also requires a lot of multidisciplinary expertise, which is sometimes hard to find and expensive. So that's an issue we deal with. And it also happens that there's no fitting vocabularies and ontologies to effectively annotate data and data sets. An example here would be, for example, climate data. If you look at something which sounds quite simple, temperature data, then well, temperature is not just temperature. I mean, if you look at climate data sets, you'll find all kinds of different sorts of temperatures. It can be observed, it can be, let's say, handcasted or forecasted temperature by models. It can be processed somehow to let's say, include effects of height differences in the landscape, or things like that. So temperature is not just temperature. There are all kinds of different types of temperature data around, and in my knowledge, there are no ontologies that go that deep and are that detailed that they can really, let's say, touch this level of detail in the data. So we run into the fact that a lot of standards are not specific enough to characterize our data. The other thing is that, well, it also follows from this climate data example. Vocabularies usually do not fit scientific requirements. Many of them seem to be designed for the annotation of bibliographic data in first instance. They're often not complete. It's often a little bit work in progress and extended step by step. So you run into situations where you see that things are missing. And we also see that they are quite unbalanced sometimes regarding the level of detail and the granularity. I think a good example from our practice would be from AgroVoc, where we used to let's say categorize and make forestry data discoverable. If you look at forestry data, then you handle tree species. I mean, a lot of the data is about tree species, but there's also climate data. So if you look at AgroVoc, for instance, then you'll see that on the tree side, the tree species side, you have a quite nice taxonomy of trees. And as an example, if you would be interested in quercus, in oaks, and you look at this structure, you can imagine that somebody who is interested in quercus is probably also interested in the level below, the different types of oaks. It could even be interested in, let's say, the siblings in this structure, for instance, Fagus, which I think is beech. So that this structure works quite well if you want to do some semantic search queries. If you on the other hand look at climate variables in AgroVoc, you can see something like this. Let's say we're interested in temperature again. If you go one level down in this this structure, you see air temperature and body temperature. Well, it's clear that an environmental scientist probably not very interested in body temperature. If you go a level up and down again, you look at the siblings, then you also run into all kinds of measures, in this case, that are quite irrelevant for our domain. So here you can see, let's say, a big difference in granularity and level of detail if you, let's say, translate the specific ontology to a specific set of domains. Well, this is just, I'm not going to dig into this because I think I'll be running out of time then, but this is a more advanced example of food production where we indeed have a cloud-based system and where we deal with all kinds of different domains like farm level information, statistical information about farms, environmental information, market information, and information about crop or animals, which is of quite different nature. Okay, the second challenge I would like to touch shortly is veracity. That's maybe one of the less well-known V's of big data, and for us it appears to be very, very important, especially because of the scientific aspect. So veracity is both, let's say, in the vertical way, the trust of decision makers that the data and the information that they're basing their decisions on is trustworthy. On the other hand, it also goes, let's say, horizontally. So people who work with data from different domains really need to be able to somehow trust the data that they're using, even if they're not experts in the domain itself. So that's quite an issue. So yeah, and it's all about trust in fact, and this is essential actually in two ways. The end users that use information and knowledge, of course, like I said, have to trust the data that has been used to generate it. So they have to have trust in the quality of the data and the metadata that's available. On the other hand, there's also the let's say the aspect of trust of the data providers themselves regarding their end users, because we also see that data doesn't get published because there's, let's say, fear for misuse or misinterpretation of data, which again, of course, is connected to the fact that if you don't supply good metadata, then it's really hard to let's say determine how data can be used, and the risk of misinterpretation is quite high. So we see that in let's say our scientific domain, data accessibility is generally quite low. It's still stored in silos a lot of the times, and well, that's also a matter of culture and policies in the research domain, I guess, regarding data management. It's in most cases only exchanged among peers in their own networks. So it's a very limited group that has easy access to specific data. And we also see that it's highly documented. So regarding the publication of data sets, like I said, a lot of data is still inaccessible in various degrees. Also for various reasons. For instance, let's say the misuse and misinterpretation issue that I just mentioned, but it can also be because scientists still want to publish on it and don't want this data to be public before they have published their research results. And on the other hand, if data is accessible, then sometimes it's not provided through standardized interfaces, which makes it really hard to process it using automated procedures. Sometimes it's also not easily discoverable. Well, a small example maybe is weather data. We use weather data and especially observed weather from weather stations and meteor stations a lot of times. And what you can see is that there's a lot of commercial interest in this data. Those meteor stations are usually commercial organizations, and they want to earn some money with their data. So a lot of this weather data is not open at the moment, which of course is for, again, a different reason than I just talked. It's just a commercial issue. Another thing we have run into quite heavily the last few years is documentation of data sets. In the scientific domain, there seems to be not a lot of incentive to provide metadata with the data. First of all, because somehow it always gets let's say an end of project activity. There's no real benefit for most scientists, at least that's what I think. So it's getting an end of project activity, and usually there's no budget anymore to do it. So it's done by somebody who does it very quickly and maybe even doesn't have really the expertise to do it. It's also boring work, especially for research, I think, so that's also an aspect. And there's usually no clear perspective on the requirements of the end user. I mean, if you're a scientist in a specific field, it's really hard to imagine how other fields would want to use your data in their specific decision problems. So, and the other thing is regarding metadata, that metadata schemas like the ISO standards and INSPIRE are generally considered too complex by researchers. So they take a look at it, they think, well, it's a lot and it seems complex, so let's not do it. So the conclusion is that metadata quality is generally quite poor. There's only a minimal amount of metadata provided most of the time, and it can be annotated sometimes, but it's hardly standardized, and most of the time it's not annotated at all. So we run into that in the building of a forestry clearinghouse, where we wanted to harvest metadata and automatically process it using ontologies and using natural language processing, which in principle could work fine if metadata was good enough regarding, let's say, the quality and the amount of metadata provided, and also regarding annotations. But we definitely run into the fact that metadata is very scarce and in many cases not good and not big enough to provide, let's say, the right base to make such automated procedures effective. So, well, finishing my presentation, something about expectations versus the current reality in our field. So the promise is that there will be a lot of new technologies which will make our life much easier. Well, examples are RDF databases, semantic technologies, things like grid computing, cloud storage solution, etc. On the other hand, the reality is that we keep working a lot with the old stuff we have. There are all kinds of reasons for that. Some of them are that let's say, the required alignment of this knowledge from different domain, and the integration are very hard to accomplish. Also, we see that new technologies work fine for, let's say, experimental cases, but also prove to be very immature, and actually too immature to be used in the real world at this moment. Production systems are consequently still developed using the things we know work well and work efficient and effective. Well, and then we come again to relational databases, legacy models, legacy data formats. And we see also that innovative initiatives usually use hybrid solutions, which are usually built on proven technologies. What I see in practice is that for instance, if you look at semantic technologies and databases, it seems to be at this point in time more effective to build, let's say, a semantic layer on top of, let's say, a classical data storage solution than using new technology to store the data, like RDF databases, which at this point seem to be not fitted at all to work with big data, for instance. So those initiatives are currently still limited to the metadata level, like the small example I used of the forestry clearinghouse. See some examples of that, and to small and medium-sized data problems, which also have usually limited domain coverage. The other promise I've called, let's say, the Googlification of scientific data provision. The promise of having transparent access to all those big data stores, heterogeneous data being accessible and combinable in a very transparent way. There's also something like the magical semantic and linguistic query processing, which people think is more or less within reach at the moment. And in fact, what a lot of our end users would like to see are tools that seamlessly transform all this different data from those big data repositories to, for example, input models, data from models, or to information for decision making on a higher level. In reality, that's still far away in our model, and we really struggle still with getting ourselves into shape for that era, I think. Like I said, already attempts are successful on the metadata level. Bibliographical resources are also quite successfully provided through those kinds of technologies. An exception might be the field of genetics, where I think they are quite far with doing, let's say, applying those kinds of technologies. On the other hand, you can maybe say that genetics is a little bit of a very specific and maybe even monodisciplinary piece of science, which can be applied to some areas, but doesn't really have the characteristics of multidisciplinary research. And I think there also is a lot of things to be done still with let's say, connecting the specific genetics to all kinds of other subdomains in animal science or plant science. So there are cumbersome first attempts to harmonize big heterogeneous data streams. We did some work ourselves in the Semagro project the last few years with, let's say, varying results. The concepts are very promising, and in experimental setup it also works quite fine, but it's not very fitted for production systems at this moment. And yeah, the consequence is that the custom-built data collection and processing chains are still dominant in our field at this moment. This might all seem not very positive, maybe. I expect, by the way, that this will change rapidly in the coming years, so I'm not, let's say, very pessimistic regarding the future. Let's say, close up this presentation, I would like to show this specific curve from Gartner, which has a lot to do with hypes and hypes getting mature through time. They have some kind of, let's say, triggering terms in this graphs, like peak of inflated expectations, disillusionment, enlightenment, etc. But I guess you can see the point here. There's a lot of, let's say, new technological innovations that are still in the let's say the innovation stage, and which might go through this curve, taking a few years or maybe more to, let's say, come to a level where they are really tested out, and where the real value and the real, let's say, application value of those kinds of technologies can be exploited. So although it on first sight might let's say seem a little bit cynical, I think there's also some let's say optimism in this graph, saying that let's say that all those technologies go through these phases, and that in 5 or 10 years they're ready to use in a combined way in our specific domain. So that's it for now. Thanks for your attention. We're open for questions now.